Good evening, everyone. Welcome to today's problem solving section, course Applied Accelerated Artificial Intelligence. So, API, uh, which actually helps us to create a job, basically is to be controlled by the master node, and which actually has to run on one of these worker nodes as a pod. Now, here this worker node actually can be a GPU, or it may not have a GPU. So in case if it is a GPU, then we have to install the appropriate CUDA drivers. So whether it has a GPU or it doesn't have a GPU, we have to set the environment for the worker node. But the effective idea is to uh, create this using a job and run it on a worker node as a pod. So this is how like a Kubernetes is set up. So the basic terms in the Kubernetes, the terminologies. Kubelet is an agent which runs on each node in the cluster and is responsible for making sure that the containers are running in a pod. So that is like a kubelet. And then we have a kubectl. This is for the communication with the CLI communication with the K8s cluster and deploying K8s objects. Next, manifest is basically the configuration as a full metadata which defines a Kubernetes object. Usually, these files are written in YAML, and there is a node which we know, which is basically a server in the K8 cluster. Pod is the smallest atomic object on the particular node. Job is a finite or a batch task that runs to completion, which launches a pod. Replicas are replicated pods in the cluster, and K8 objects to maintain API keys, passwords, and all this the password API keys. And next is secret. K8 object to contain secrets, password, API keys, useful for storing the NGC API key. Next is services. K8 objects which describes how to access applications can be used to expose a port on a running pod, define a load balancer, etc. Deployment. K8 object which encapsulates an entire application. Next is Slurm. Slurm is simple Linux utility for resource management. Um, it is for scheduling, used in the HPC resource management and job scheduling. But when Kubernetes mm, does so many things automatically. Let's just go to the one is the Kubernetes way of implementing, and the other is the Slurm way of implementing. So in Kubernetes, share nodes, which schedules the job for the GPU on the node. It's like giving permission security. You can do analysis, monitoring, and advanced is Slurm. It is for multi-node jobs. Example DAGs, DAGs. And then we have reservations, which is that we will see in the future classes. Ticket reservation ticketing, scheduling. Kubernetes is used for the cloud like situation. So it is a service oriented. It is containerized. It can be scaled, and it does not. It does the load balancing on its own, and it will ensure that the quality of the service is maintained, and it keeps the application running. And whereas the HPC uh, is for the batch type work, batch type job oriented things. So it is run on a bare metal, and allocates resources and the right user and the user control. It can be, it's a fine grain user control, and maximizes system utilization. Next is DevOps. DevOps is a set of practices that have been made it possible to ship software to production in minutes and keep it running reliably. So, like there are two things basically, which is development of the software, and another one is the operation of the software. So, development and operation. So when we mix both of them, it becomes DevOps. If we have a software, like we are developing it, once it is developed, it has to be operational. So this is what is DevOps. Um, so if we see in the development portion, it is plan, build, code, build, and test. Then once once the software is complete, released, it is going to the operational phase. So we have to release, deploy it, operate, and monitor. So this is the operational part of the project implementation, where this is the development of the project implementation. DevOps is going to actually help us coordinate between these two phases. When we say coordinating between the two phases, DevOps is going to rely on tools, automation, workflows to abstract away the accidental complexity. So the idea is that it ensures that automation and workflow is actually implemented, or like we are able to implement it without any complexity, Yes.
అమ్మ ఇక్కడ పెట్టిన చెప్తుంది తీసుకుంటాను నేను వర్క్ ఉన్నాక చెప్తాను పడేసావా ట్యూబ్ రెండోసారి పడేయడం నాన్న విరిగిపోతే ముక్కలు ముక్కలు అయిపోతుంది
So next is MLOps, the next version of DevOps, when actually the machine learning deployment, and then we will see the deep learning deployment. So we call it MLOps. When we say MLOps, it is like actually develop DevOps, because we are trying to develop our software or deploy the project at the same time. We have like to implement it, deploy it, see it operational, and like see the people are using. Now it's like two things, deployment and operational, and it is related to machine learning. So it is
పంపించిండు
called
ఏదన్నా
MLOps. Now what is the difference between MLOps and DevOps? ML projects are managed and operated. So here we have, along with the code,
043 yes తప్పు 094
so machine learning projects or machine learning software, it is not just the code, but it is also code plus data. So it's like we have got the data, the program, and the application code, and then we are trying to train, like do the training process,
అరే చూద్దాం ఏంటివో ఇది
and some model we have. So the software code is, the code is along with the data to be used. So what is the main difference between the DevOps and the MLOps is the data. And then next we will see DevOps. It is like more complicated in the sense that when a project is developed, to maintain it, to operate it, to operationalize it, it is like next level of the MLOps. So in all these three cases, Kubernetes is the major security block, which ensures that it it can operate, it can
483
deploy, it can schedule, it can coordinate,
345
orchestrate, and all of this.
2 కాదు 3 4 కరెక్ట్ 483 345
So we have the code. The code is written in a restricted development environment, and data is generally from the real world. So MLOps is a set of practices that combine machine learning, data engineering, or data processing, and then this is like what DevOps. So MLOps is a set of practices that actually combines the machine learning, data engineering, and DevOps. So actually, MLOps is a set of practices which is combining machine learning, data engineering, and DevOps, which aims to deploy and maintain machine learning systems in production reliably and efficiently. So So there will be a data pipeline, a machine learning pipeline. So pipeline is a basic pipeline which is a series of transformation that are applied to the data between its source and destination. So we give our data as an input to one of the sequence of modules through which the data has to pass. It has to come to the destination. So in between, whatever is that pipeline is basically becomes a data pipeline. Now ML models require some type of data transformation and it depends on our application, but it requires some type of data transformation. This type of data transformation either we write in some script or some cells in the say Jupyter notebook, or like it, which actually makes them hard to manage and run reliably. So our machine learning models will require certain types of data transformation which we generally do right, and there will be so many cells which do this transformation, but gradually in the long run how do we manage them and run those things reliably, that is like very important. So using proper data pipeline provides many advantages in code reviews through runtime visibility, management and scalability. Also it improves it actually improved uh, like how to design a data pipeline, and then how do we ensure that the ML transformation and this pipeline are actually coordinated. So most versions have two pipelines, one for training and the other for servicing. So this basically means that when now like our application which actually has to do some task like classification, object detection, recognition and some number of some application, it will have two pipelines, one for training and one for servicing. So So when we are giving some application to a people to use it, then that is a testing phase of our application. So we want people to use it so that it is like where service comes. So the ML pipeline is pure code artifact independent from specific data instances. So ML pipeline does not have any interference with data pipeline. Whereas data pipeline is totally separate from the ML pipeline. So we assume that there are two pipelines for training and one for servicing. So ML pipeline for training and for servicing. So how like we take the data and transform it appropriately. There is an ML pipeline. There will be a model which will be trained using this type of training mechanism. Then we have a code which will be actually training the this developing model. Then once this is completed, the data to the servicing pipeline, and this if this is completed, so we have CI/CD, combined practice of continuous integration and either continuous delivery or continuous deployment. So we should have a continuous integration and should have continuous delivery, should have continuous deployment. All this go hand in hand, but should ensure that everything happens so seamlessly smooth that we will try to actually synchronize things and then do basically these things efficiently. System for synchronizing and orchestration, etc. Next, DevOps, MLOps. So it has a bit of similarity between DevOps and MLOps, and what are the differences between both of them. So DevOps are developed to maintain version control, a good pipeline to understand behavior validation, CI/CD, continuous deployment, then the data validation and monitoring. So MLOps and DevOps actually are used in the version control, code version, data lineage, code version control plus data versioning plus model versioning. So like people have started developing the code version controls on DevOps because at this time like this is only DevOps. Then we had data lineage also linked to the code version. And so we went mixed both of to get the ML of ML type. So when we talk about the pipeline, initially DevOps did not have any concept of pipeline because we only had to ensure version control. But when we talk about data engineering, data pipeline, the extract, ETL, etc. So the data engineering it came into the picture. In the ML ops was bit modified into training ML pipeline and serving ML pipeline. So then the behavioral validation, here we have unit test, but in the case of the ML ops, it's the model validation. And when we talk about CI/CD, deploys code to production, deploys data to the pipeline, deploys production plus training ML pipeline. So these are certain like differences. How do actually try like how they try to do these things. Then validation. Uh, Data needs to be validated. In case of DevOps, there is no data, so it's not applicable. And so there is in the case of the MLOps, statistical validation, and here format and business validation. When and next is monitoring. And in all the DevOps, data engineering, and MLOps are called as that the service level objectives. So SLO, service level objective agreements. So in the case monitoring was done on service level agreement types here also and here also. And in the case of MLOps, there are service level objectives, service level agreement. Then there is something called as differential monitoring and statistical slice monitoring. This basically is an advanced version of trying to monitor things. Next, DevOps. Okay, we saw the DevOps, then we saw the concept of MLOps. Next is the concept of DeepOps, which actually involves deep learning. Since deep learning is involved, we could have a lot of GPU. So those GPU can be of anything, making and DeepOps is an open source project from NVIDIA which facilitates deployment of multi-node GPU clusters for deep learning and HPC environment in an on-premise operational air-gapped data centers or in the cloud. So the idea is we can have a physical or premise data center or basically in the cloud. So this is an open source project. And this is actually used for managing pods on the DGX. So this is the GitHub link for the deep DevOps. Uh, deep DevOps. Okay. So what is it? There are so many things which DevOps can do. So it can do job scheduling using Kubernetes, Slurm. You can maintain the uh, firmware of the DGX, monitoring using DCGM. Um, you're saying this. So going to the architecture, uh, so we have got the Kubernetes node, and these Kubernetes node are actually part of the compute nodes. So we will have a Slurm node. The Kubernetes nodes, we will have a Slurm node, we will have a Kubernetes node, because we know that any Docker which is not generated by the Kubernetes is not going to be maintained by the Kubernetes cluster. So we can actually take a Docker image and run it. But if Kubernetes has to manage it, it has to actually started by the Kubernetes through a Kubernetes image. So something like this. So the hybrid strategy. Now the idea of a hybrid strategy. So we have the augmented legacy of the HPC schedulers with the new features. So we have cluster management services. We have like Jupyter Notebook. We have deep learning inference deployment. So like if we are doing inferencing is like a servicing pipeline. So we use like tensor RT. Basically means should ensure how do we deploy it. So we also see that how the data has to be kept in the same place. No need to have like separate clusters. So there Kubernetes, so like the Kubernetes managing the cluster infrastructure is it can run some workloads. We will have DL inference tasks. Say we can run Jupyter Notebook. We can do multi GPU, multi node deep learning training. We can do tensor board. So many graphs, charts. So Slurm runs HPC workload. These HPC workload traditionally are non-containerized workloads. But nowadays we have a lot of HPC containers. So whatever people used to use like a lot of containers which is like now changing. Hyper-Kubernetes and Slum clusters. So this is how we stack up the software stack. So we are trying to develop a hybrid Kubernetes and Slum cluster. So here DHCP container, Grafana, alert manager, Kubernetes, then Slum login node, uh, the DGX, the compute node, and then the management node. Building the cluster management nodes. So we should have, for when we are trying to develop our own cluster, we must have one management node which actually has the OS installation and Kubernetes bootstrap. So we have to install and integrate, and then there are certain like container. Uh, so this with Kubernetes and cluster services container develop. So we have the uh, management node, we have the login node, and there are various ways of trying to actually do software installation and bootstrapping of the login node. So, and then there is a compute node wherein we need to install Kubernetes again and then bootstrapping it. Okay, so next we will go for the design principles for building high performance clusters, networking fundamentals. The This is the first Cray machine which actually enables connecting uh, 4 CPUs together, and all the 4 CPUs shared a certain central memory, and they are also connected to each other for running the parallel workload. And to connect all these elements together, there was some interconnect CPU communication and control. There is where network for HPC comes into picture. We need some sort of mechanism to distribute the workload between the various CPUs, and we need to have this mechanism to coordinate between the various compute elements, and we need the mechanism to do some sort of memory locking, so that if one element is writing on a certain section of the memory, then the compute node could not be overwriting that on the same memory. So now this is a traditionally how it started. So we cannot be keep on adding more and more CPUs. Like we see over a period of time, if we keep on adding more and more CPUs, we cannot because of the complexity it that is required to connect them together, and it starts to increase manifold. The central block that is interconnect, the inter CPU control and communication part, it becomes more and more complex. And there is only a certain limit to which it can handle the number of the compute nodes. And this is where the industry started moving into something called clusters, and started from this is how like standard typical SMP machines to this large modern supercomputing clusters is the journey of various technologies. So in a modern supercomputing clusters, we have to do like hundreds or thousands and even of thousands of these compute elements. But now they cannot all connect into a central location. But imagine what is this central location. It is all some sort of logic. It is a silicon device which will coordinate between all this. Now imagine if we have to connect 1,000 processors to a single silicon, trying to coordinate and do data processing between the compute elements, it is impossible to construct. And that is where the standard high performance networks come into picture, where now we are able to link tons and tons of CPUs together to create a single large supercomputer. The programming paradigm, the use cases have changed like quite a lot, because if we look into a standard symmetric multiprocessor machine with where whole set of RAM was completely shared and between all the compute nodes, we cannot have it in a clustered environment. So the new paradigm of exchanging data came into picture, which is called message passing, which most of the people who are into HPC domain or AI domain are aware of it. So we have a sort of communication library that packetize the data from one CPU element and then send it across to another element, and it does it using some sort of messages, which is what we call as MPI, message passing interface. So to do all that, we need to have a basis of connecting all these elements. So MPI is message passing interface. So to all this, we need to have the basis of connecting all this element. And when we say message passing, it is very higher layer of abstraction. It is the domain of coders. But before that, we need to create a cluster. And that is what we will talk about from the fundamentals, and what are the design principle, what are the limitation, and what limits us going to this. Network component for high performance clusters. So why we need networking? We need networking because we have a large enough job which cannot fit into a single compute unit. So we need to distribute it among multiple compute units, and therefore we need multiple compute elements, and some sort of interconnection is required to connect this with the another element. Now, since the cluster is not only a point-to-point connection between two elements, we need to have hundreds or maybe thousands of compute units, and we need to have central interconnect unit, which is where we bring in a switch, a network switch, or a combination of multiple network switches. And therefore, we need to have a end interface device which is called network interface card, or a host channel adapter in various technologies. it is nothing but an interface which is kind of uh, processing element is able to address the memory of processing, like a processing element, and it's able to send data from its port externally to a particular switch which will receive the data, try to make a process like where it should go, and then send it to the across to its destination. So there is an element inside compute node which is called as a channel adapter. Sorry. Okay, which is called as channel adapter or a network adapter. There is an interconnect media which is our cables, and there are switches, and this repeats till the destination. HPC interconnect history and development. So if we look at the HPC interconnect history and development, it starts from 1995, where we had Cray as one of the leading supercomputing companies. They started off with a crossbar interconnect to link multiple of their compute elements. Then there was an explosion of multiple standards and technologies by the end of 1990s. So towards 1999 and 2000, there are companies like one, two, so many companies which started to standardize high performance interconnect for HPC and HPC clusters. And there was no AI back then here. So now when AI came into picture, we will uh, like talk about how the fundamental requirement of AI are completely equivalent to what HPC system needs. So the system that we design for HPC now are actually being called HPC or AI systems. So many companies started off, and there were a lot of standards. The whole aim of all these standards was to have the fastest possible pipe between the compute elements, so that we can transfer the highest amount of data passed in the least amount of time, which corresponds to the our bandwidth. So it is aimed at reducing the latency of this transfer, because every time when we are doing a parallel compute loads, there are like very large data transfers. There might be simple communication wanting like a small communication, say simple flat communication or data exchange. So the network like be very low latency, because whenever there is a task that is spent by the data in the flight in the time is the time no compute can happen. If we are looking at synchronized compute and communication, the time spent on moving data from one point to the other point is time wasted. So we have a very little small latency as possible. So the fundamental of high performance networks for building clusters was high bandwidth and low latency. And over the years, many companies did a lot of the things. Now, in the today, two companies uh, Are there in InfI so InfIBand is like commonly InfIBand. Okay, going to the fundamentals of physical layer. At the physical layer, it is like a wire. So we take two elements and we connect using a communication cable between them. So it should be able to transmit zeros and ones, like a sequence of zeros and ones. And we most commonly like use for the standard LAN cable, RJ45 cable contains copper conductor inside, and there is a certain speed at which we can send the bits, like send zeros and ones. So today we are looking like sending at 12 gigabits per second or even 50 gigabits per second. And depending on what kind of signaling we are doing, if we are doing non-return to zero, where 0 corresponds to 0 volt and 1 corresponds to high voltage, we can divide the levels as analog signal by multiple levels, represent every level to a particular bit pattern. So this is the amplitude modulation. The media that transmits the data between the, but it is like a media that transmits the data between the two components, compute elements. That wire is a like a media that transmits the data between the two compute elements. So what we don't want to achieve, it's like there are so many standards, say 14 standards, and then standardizing it, one more standard came. So total 15 complete competing standards. Okay, connectors, evolution, and need. So this is like physical media connectors. Say standard LAN cable, RJ45 volt. So it consists of multiple copper conductors inside. So in HPC or AI clusters, we are looking for like 400 gigabits per second. This standard links are not capable of carrying that much. So we like therefore we have standards which are based on SFPs, standard which is based on QSFPs, SFPs. There are These are various connectors which are used to link two systems together or link a system to the switch, and they have different capabilities. But the fundamental capability comes from the fact that we need to send data as fast as possible. So the interconnect speed and modulation. So we can encode more rather than having the voltage level 0 and 1, so that carrying 2 bits in every clock cycle. So increase the clock cycle itself rather than clocking data at 25 gigabits per second. So we will get 50 gigabits. Next is we can use multiple physical channels so that when we connect two system together, say from we are going from normal RJ45, there are four twisted pairs. So it is like unshielded twisted pairs. There are four pairs of copper. So we can have more parallel lanes to increase the bandwidth. All next is going into the optics, multiplexing multiple wavelengths into a optical fiber. So all these parameters have got certain limits and like limits related to the current technology. So let's look at the standard high speed uh, channel between transmitting element and the receiving element, means between the server 1 and the server 2. This triangle is a transmitter. It represents the black box. It goes from into a connector, and the connector goes into a channel. The channel can be a cable. It can be a large supercomputer where you plug in multiple servers, or the channel that carries signals. And there is a connector, receiver, connector, and then there is a receiver amplifier, and therefore there is entire thing of high speed channel. So next is eye diagram. So when we are sending data on this high speed channel, we will be sending it zeros or ones. We have seen like interconnect relate interconnect papers having this kind of eye diagram, that whenever there is a high speed network, it shows a diagram which looks like an eye. So every 0 and 1 has got a bit period. So the period of this bit is nothing but the reciprocal of the frequency. So if we are transmitting data at 25 gigahertz, the bit period is certain amount of nanoseconds. So if you plot all these bits in that window and then overlap all the other bits, we will be seeing something which looks similar to I, where x-axis represents the period of the bit and y-axis represents the amplitude of the bit. So this looks like an eye. This diagram just like represents if there is a 0 or if there is like which is mapped to a negative voltage, and if it is 1 it is mapped to the positive voltage, and there is a margin between where no bit is present, or like no sample is present in the in that margin. That means my receiver can distinguish between the 0 and 1. So so because the voltage levels are distinct, and if I have a comparator, we can uh, say it is a 0 level or a 1 level by comparing the level crossing. When we are transmitting this data through a channel, the bit period or the eye diagram starts looking somewhat like this, or like this. And the eye is, this is, so there are some places called where eye closing. What is now meaning is that at the receiver end, like say consider when we have a long channel, the eye completely closes, so there is no more black portion in the center over, see, like here. Therefore, my receiver cannot make out whether it is a 0 or 1. So this defines the limit to how many, like the fundamental limit. So unless and like it is able to make out between 0 and 1, um, we are not able to like transmit the data between the source and the receiver. So what is insertion loss? So when we start increasing the frequency of the electromagnetic wave that we are transferring, the amount of resistance that it offers is also increased. There are more losses and channels are not capable of keeping up to the certain speed limit. So why are they not able to keep up to the certain speed limit? Because of the its physical properties. And there are copper loss, there are reflection. So when we look at the bit diagram, there there are multiple zeros followed by multiple one. It is very low frequency because the time period is high. When the bit pattern is continuous sequence of 0 and 1, the frequency is high. So actually like we are transmitting wide range of frequency, it is a wide band. So when we transmit the low frequency, the attenuation of the media to this frequency corresponds to this side of the spectrum, the left of the spectrum. And when we go to the high frequency, we have more attenuation, and this is the property of the copper conductors. And when we are transmitting an electromagnetic wave, it is a transmission line. There is a dielectric and there is a ground reference plus minus and dielectric in between. When an electromagnetic wave is going through the media, the dielectric also needs to polarize and depolarize at the frequency at which the transmitting the wave. So this dielectric ability to polarize and depolarize causes frequency dependence of the insertion loss, and because of which high frequency get attenuated more and low frequency gets attenuated less. And we see the eye closing. So these are the limitations. And moving into the optics, because insertion loss in optics is very less. So when we are sending an optical wave, it goes through optical fiber and like we do not get so much of insertion loss. So now we can carry it for longer distance and carry with more speed. But when you go to the optics, we need more power, more energy, and more complicated electro-optical converters. So how we launch the data into optical fiber? Through laser, which is being turned on and off at the same frequency as our data rate. And the laser, when it turns on, it sends a pulse of light, and the photo detector detects it and then converts it back into electrical signal. Like say when the laser is on, 1, when the laser is off, it is 0. And there are other technologies like photonics. Um, Instead of turning on and off the laser, modulating the laser so that they operate in a region where lesser delays between turning on and off. Therefore, we can transmit the data faster. So starting from the standard LAN to like that telephone cables which had the speed of kbps, and next UTP connectors which give up to 100 mbps. So starting from today, like a single port's link speed of around 400 gigabits per second. So this is where we solve the bandwidth problem, and the development going on in which we could actually increase it from 400 to maybe a tera per bit per second and beyond. So next is network layer and routing. So till now this was from the physical side. So on top of the physical layer now comes the network layer and routing. So let's take a switch element, say InfiniBand. It is from NVIDIA. NVIDIA uses InfiniBand, and also other kind of interconnects like NVLink. InfiniBand is like constitute around 99% of top ranking system um, switch. Actually, it is a silicon device which has multiple ports. Um, like as we can see in the front panel, on these ports we can connect the physical media like the copper cable or the optical transceivers. The transceiver or the copper cable is receiving data from one server. The data comes in at a very high rate, and we are looking at one say 200 gigabits per second. The data comes in, and now the silicon needs to perform the required operation on this data. And it comes with a sort of header. Header contains the source, destination, the source address, and the destination address. So the silicon inside the switch is required to look the destination, and then it is required to check from which port it should be send that data out so that it will reach it to the destination. For doing all these checks, we need a sort of table, so that the table needs to know to reach a certain endpoint and what port I should use. Like this is the concept of switching and routing. And the time taken for this silicon, or the time taken for this ASIC inside the switch to take a packet in and decide where to send it out and to send it is known as latency between the two ports. And this is again one of the important parameter for high performance networks, and it is in the today's term, it is in the order of 130 nanoseconds for this particular switch. That means one data byte comes in, or a packet coming in from port 1 after 130 nanoseconds will appear outside a destination port. Next, designing small HPC AI clusters. So if we need to create a cluster, small cluster will take multiple servers, and we have to like connect it all to that particular switch. Say So it is not like a single switch. It is actually a big device which contains multiple ASIC inside, and they are connected to each other in certain way. A single ASIC, there is a limitation to how big an ASIC you can make. Uh, like one of the simplest limit is the die size. So like what is the die size, and take a large wafer to get a good amount of yield, you will like have a certain size of a die on it. So the certain size of the die will be able to service only certain amount of ports. Fine, like we need electrical signals out of that die. How many ports we can take out of that die will depend on how many pins will be coming from that silicon, will be taken out from that silicon. So the largest port count processor network processing that we see today is of the order around 40 ports or 128 ports, ranging between them. And of and there are clusters containing thousands of compute elements. So a chip which has only 40 nodes, how we will be able to for the 1,000 compute element? So how will we be able to connect thousands of compute elements? So we start making the topologies. Topology is a high performance computing cluster and cannot be random. So next, the internet, the World Wide Web is also in a particular topology. So every endpoint is connected to every endpoint through some link. So in a HPC cluster, it is not some random connection. So here the aim is that all the compute elements, it has a kind of capability that uh, they should have the same kind of network bandwidth, latency, and delay. So therefore, we need to connect them in a well-defined manner, because we like one another reason that is like we need to connect them in a well-defined manner, because we like have to have the we want the communication in a symmetric way. So the network topologies. So this is like equation defined routing between the elements. So there are various kinds of network topologies, at like standard tree topology, fat tree, hypercubes, t- torus, dragonfly. What is the common difference between all this and the World Wide Web mesh, random mesh? The difference is that all these topologies are very nicely mathematically defined. Therefore, like we have defined routing between all the elements which constitute this particular network. And this is where the network layer and the link layer comes into picture. So these are some examples of topologies. So if you want to make a large cluster, we like end up putting multiple of these switches, and we will be connecting them to each other in a particular fashion. So we will create multiple layers, and therefore we create large clusters. And say talking about this three level close technology. So now if we say connected only two switches, the maximum compute that we could connect is equal to the number of ports of these two switches minus the number of ports which are required to connect the two switches together. So if we have 44 port switch and say 40, say maybe we can connect 40 30 servers to switch 1 and 30 servers to switch 2, and there are 10 links between the two switches. So if we grow more, we can create a triangle or ring, and further it will be a tree. Here every box represents a switching element and every arrow represents a link. This is a switching element, and the arrow represents the link between the switching element. And then we keep on folding this connection, and we create a well defined uh, mathematically explained topology. Therefore, we actually put this equation into routing engine of the switching element. There with um, like it will know where to send the incoming packet if it has a certain destination address. So high performance network needs this deterministic routing, and there are now adaptive routing as well. Next is Dragonfly. So at the bottom line, the takeaway is that like high performance clusters needs the network to be well defined so that the routing elements are like they contain the routing table which is given by the equation so that they can send the packets without any issue or delay. And also we whatever we are creating, we don't want any packet drop. Uh, like in Ethernet, packet drops are allowed because it connects to the entire like world wide web. We know there can be conjunction, so if we know it is not like 100% reliable thing, if there are problem in the middle, we can drop some packets and the software can request for retransformation. But in HPC, if we have the software trying to request for the retransmission, the whole process will become slow, and like this we cannot scale the application. So we need the routing which credits based on every element knows that it has got a path available to its endpoint, and therefore every source can send data to the destination without packet dropping. So in InfiniBand packet format, so like we are sending zeros and ones, which are like bytes put into packetized format from the server. So the packet contains some delimiters to tell the server that one packet is coming. Send it out. It will contain a local routing header or a global routing header, some transport header. So some transport header, and it will contain some local okay, transport header. So based on the standard OSI 7-layer model, which is actually the basis of for most of the network, or like all of the network. So there will be some identifier which says so like where is this packet coming from. The main payload is in the center, but there are bytes which define from where this payload is coming and where the payload is intended to go, and what kind of operation it is. So all this comes inside the packet format and comes into the network layer and the transport layer. So till the physical link and network layer. So next is transport layer. So this is actually the TCP IP, the application which is a routine which contains data in a particular buffer, and that buffer is part of the say the RAM. The application copies that buffer to the socket. Uh, so the socket layer copies the data from its own buffer to the transport layer and the protocol drivers inside the adapter in a server. The adapter breaks it down into an Ethernet. We will call it as MTU. So it has to break into a particular transfer unit. Then it will send it out through the physical adapter through the cable. That is that interconnect medium, and there can be switches in between and connected to various topologies. So the job of switches is to look at the source and the destination route it according and route it accordingly. Um, so let us assume it is routed correctly and it has reached the destination. The destination again, there will be multiple copies of that data coming from various portions in the buffer, and the data will reach the target. This whole cycle of copying data from server to the client or the server number 1 to server number 2 is called the latency. So let's say if we want to send one floating point number in double precision floating point number from server 1 to server 2 in the TCP, it will take microseconds. The TCP IP based connection will take around 10 microseconds because there are so many buffer copies are involved. Therefore, for high performance network, we need to have the transport layer which bypasses all this intermediate uh, entire like bypasses the entire kernel driver and the protocol driver and the buffer copies, and which is where an example like InfiniBand, which does something called remote direct memory access, RDMA operation, where it actually reads data from the buffer of one application, which is the in the RAM of one application, and put it to the uh, RAM of the second application, because it is able to do the latencies are in the order of some microsecond or actually hundreds of nanosecond. If we have like two servers, say two GPU enabled, and so if we try to like connect them, we will be able to like get around 100 to 700 nanoseconds because we are able to bypass all these points. So GPU direct RDMA. Think it's opening directly. Next is the latency. So here, like in a typical like high performance computing operation, we are making these clusters, connecting all this compute together, and we can run a very large say job by dividing into multiple compute units. So any application which is trying to solve say even uh, sim- partial differential equation will be containing like a matrix vector multiplication or a matrix sparse vector multiplication. So which will not fit into a single system. So we will be breaking it down and send it across multiple systems. So when it is sent to multiple system, they will have all compute their portion. After they have computed this portion, they will try to exchange the data to each other, and they will try to send their results to some storage. So there are the operation in which we could distribute data and collect the data like one to many, many to one. This kind of operation in networking domain are called collective operation, and it required for every iterative solvers. So still okay. Let's solve the previous year assignments. Then we will come back here. Which are the important characteristics of HPC and AI system networks? So low peer-to-peer latency and high bandwidth. So it is critical for fast data exchange and yes, and efficient processing, and the low over subscription of relatively non blocking, which ensures minimal congestion and bottlenecks. Next is the ability to scale to large number of endpoints without needing complex routing mechanism. This is also important for large scale systems to maintain efficiency and simplicity. So yes, going to the next question. Which is the most popular fabric topology used in the current generation of supercomputers? Okay, the answer is battery network. This topology provides scalable, non-blocking, and high bandwidth connectivity, making it widely favored in the modern HPC systems. 60 torus topology connects nodes in a multi-dimensional grid with a wraparound link, like we have seen, like wraparound link. So this is used in some of the HPC systems, but it's more complex wiring and longer cable length. It will require more cable, longer cable length has the it dimension increases. So it is less flexible for scalability and it is harder to maintain low latency. Hypercubes connects nodes in an n-dimensional cube structure. So it is good for small to medium clusters, but it becomes complex for larger scales. And Dragonfly mesh topology is designed for scalable high radix routers and aims to minimize the number of hops, but still like it is less widely adopted and more complex in routing and implementing. So it requires advanced routing algorithm and a specialized hardware. So that's why it is like a factory network, which is scalable, non-blocking, like low blocking, ensures high bandwidth, low latency, and widely supported by hardware vendors and network equipments. One second, I think what is InfiniBand? Yes, it's factory. Okay, going to the next question. Which statement best describes RDMA? RDMA stands for Remote Direct Mapping Access. So the answer is only two. Yes, because remote direct memory access, like the capability of HPC network, transport layer to directly access, read or write remote signals from the memory. So it is not about like random access across the cluster. So this statement is wrong. RDMA allows one compute to directly read or write memory on another compute without involving the CPU or the on the remote side. So reducing the latency and CPU overhead. So this is correct, and is not for any accelerating the TCP/IP stack. So by offloading the network adapters. So actually, this is describing some technologies like TOE TCP offload engine, but not the RDMA itself. So this is also not there. So only two. Going to the next question. What does NVIDIA Scalable Hierarchical Aggregation and Reduction Protocol aims to improve? Yes, performance of MPI and machine learning collective operations. So, like this protocol is designed to optimize data aggregation and the reduction task commonly used in parallel computing and distributed ML workloads. So it is option C. The next question. An InfiniBand switch is a device that routes packets between it routes between nodes that are in the same InfiniBand subnet. So like InfiniBand switches connect endpoints to within the same subnet to enable the low latency, high bandwidth communication. So it should be in the same net InfiniBand subnet. Yes, option C. Next, which is not the correct mechanism to increase network bandwidth on the physical layer. So, which is not the correct mechanism to increase the network bandwidth on the physical layer. So, increasing the clock frequency will increase the rate at which the data is sent. Increasing the number of lanes or the uh, channels, like multiple lanes in a PCIe, increases overall bandwidth. Next, using advanced modulation schemes like PAM4 increases bits per symbol, boosting bandwidth without increasing frequency. But increasing the transmission amplitude is the signal strength, does not increase bandwidth. It affects signal quality or and reach, but not the data rate. So the correct answer is the option which is wrong is increase the transmission amplitude. Okay. Next question. In a GPU accelerator cluster, what are the most important network characteristic affecting overall system performance? So the most important network characteristic affecting overall system performance in a GPU accelerator clusters are balanced GPU, network bandwidth to keep GPU GPUs like getting that being fed optimally. And next is RDMA, access directly from GPU high bandwidth memory for efficient transfer. And next is multi-rail connection to increase bandwidth and reduce bottleneck. So yes, D. The next question. Which element in an HPC network contributes maximum peer-to-peer latency? A 5-meter cable between the server. So the latency is very small in the nanosecond range, because so this is not. The next is memory RAM latency is local to the server, and so it should be faster than the network delay. Next is interconnect switch between port to port latency is low in high performance switches, often like between sub microseconds. When it is in an adapter, NIC processing plus MPI software, overhead has significantly, so the latency due to data handling protocol, CPU involvement, making it a largest contribution. So the in the end-to-end peer-to-peer latency. Yes, option. The next question, ML flops includes. So the first one is continuous integration CI. So automating integration of the code and the ML model. So yes, it is included. Next is CM, continuous monitoring. So monitoring model performance and data drift in the production. Next is CT, continuous training. So continuous retraining models with new data. CD, which is continuous delivery. CD, automating deployment of the model to the production. So all the four. Yes, all the four. Next question. Which of the following are true about deep ops? So the deep ops facilitate deployment of multi-node GPU clusters. So it is recognized as DGX pod management.
Ma'am, not visible. Your screen, it's not visible.
Screen is not visible.
No, it's stuck in the question number 9.
Okay, okay, sir. Yes, I think now it should be visible.
Yes.
So ML ops includes CI, CM, CT, and CD. Next, going to the question number 10. Which of the following are true about deep ops? So it facilitates deployment of multi-node GPU clusters. Like, and it is recognized as a DGX pod management software. Uh, but supporting the configuration where both the Kubernetes and Slum run on the same physical layer is not a standard feature of the standard feature of the DevOps. So running Kubernetes and Slum side by side on the same node may require some careful resource partitioning, scheduling, and some custom integration. So it is not like directly provided by the DevOps, but may be possible. So it's so one and Yes, one. This is my understanding. I hope it is correct. Yeah, one. Yeah, because running Kubernetes and Slum on the same physical cluster, which is not directly given by the DPops, there can be some custom integration, but not directly given. So, like it can be technically possible with heavy customization to run both on the same clusters, but DPops doesn't natively support or like recommend this configuration. Is it clear? Fine. Any doubts? Okay, I just skipped some slides in between, so I will just take up that now. I'll just start with this sharp scalable hierarchical aggregation and reduction protocol. So it is like actually we are going to use the networking element to also take part into computation. Computation, not like any mathematical computation, but the computation which are network oriented computation. Like when we are trying to run the reduction operation, the switches or the network switches themselves are actually collect the data in a single step from all the connected slaves and do a reduction. Reduction can be simple sum or minima or local minimum maximum or XOR or AND operation, and like the operation which is demanded by the applications. So every switch in the network can take data in a single step because all the servers which are connected to it are connected in a parallel way. So in a single step, it will be able to receive data from say all the servers, say n number of servers. Now n is equal to the number of servers connected to that single every switch, and we'll do it in a single step. So it will do the operation and then send the result to the next switch. So now we reduce n step operation to a two step operation. The two step for network size and topology, which is two level. Like this is one of the advancement in the networking, like integrating the compute element so that high performance codes can be accelerated by offloading certain things into the network itself. And when like because we are able to do it in two steps, the top level switch is able to now share the aggregated result in a single core, but all the lower level switches can collect the data in lesser number of steps. And this graph I will just skip. So like this is, say we have MPI weight. Uh, if we like do MPI reduce, there are, so there is a system calls made in the system called API weight, and say we need to reduce this, like say some broadcast, or we need to do some point to point, and we need to reduce all this. So the say this dark green, which is MPI reduce, which is in the dark brown is all MPI all reduce. So we need a particular runtime, say almost 20% of the time is spent doing the reduction, and also this weight. So weight is one of the main thing because most of the jobs are like have to run on the compute and communication has to synchronize. So we see there are collectives as well. So there are so much of broadcast uh, in the blue part, and there are some like all reduce reduction, and the reduction was only 4 byte and 8 byte. If you see that green line here. So if we are able to do this particular portion of the network, we will reduce this 20% to say less than 2%. Network has actually helped in accelerating the compute. So it is like intelligent network, not doing only packet passing. It is like getting intelligent networks. Yeah. Okay. If you have any doubts, you can just post. We can discuss. Any doubts? Okay, so we have say a set of data, and there is a parameter server which actually looks at the every iterative step. It looks at all the data input and tries to train itself by getting a new weight and tries to assign a weight. And this weight is a calculation done by collecting data from everybody, the delta from every input, and then calculating a new weight factor and then distributing the new weight factor. So then again the next training cycle where every agent will give its own delta weight to the parameter server, and then the parameter server will do some operation and again it will try to fine tune. So this is again the way a kind of operation like iterative, and therefore it can be mapped onto network acceleration, which is done by the current intelligent networks. So this is NVIDIA's GPU, current generation NVIDIA's A100 GPU. It has certain amount of like teraflops of floating point 64 performance, and multi GPU communication to solve some of the jobs. Next is So this GPU is then put into a motherboard. Multiple of them are put in the motherboard in the form of GPU accelerated system. All these GPUs are connected to each other using high speed interconnect, and they exchange data between like each other. So when we want to uh, say have more than 8 GPUs for the training workload, say clusters supports up to say 500, which have got like thousands of GPU doing a single job. So we need to go from 8 GPU. So here we connected 8 GPU in a single motherboard. But if we want, then we need a network card. So there are multiple network cards over here. They are connected on the motherboard, and it is a form of full GPU accelerator system. This is one of the particular building block of supercomputer. So many GPUs on it and so many network cards on it. Uh, so this is a logical connection of various elements. It contains the processor, contains PCI Express switches, uh, any like, and next is mapping rails to VI trees. Yeah, so if you have any specific doubts, we can discuss. Otherwise, we can end today's session. So this is like for the fault recovery. In the normal TCP IP, like if software layer will come and that there is a packet loss, so the data will be transferred. But here there is a mechanism like for the fault recovery. Yes. So, yeah. Any doubts? Okay, so if no doubts, I will stop the recording.